We just saw in the previous lecture the definition of total dual integrality, and an important thing to notice is that this is a property of the representation, not of the polytope. So what do I mean by that? I mean that, what did we see? We saw that by the definition, if AB is a system that is TDI, and in particular B is B is an integral, then this implies that this polytope is integral. That is the main property of the definition. But the converse does not need to hold. So let's look at that example that we've mentioned before. So P is equal to the intersection with the non-negative orthant of the constraints x1 plus 2x1, plus 2x2 less than 6, and 2x1 plus x2 is less than 6. And just drawing this out again, this is 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. It goes through the points from 6, 0 to 3, 0 and 0, 6 to this. So it is this polytope. I didn't draw very well, but this point here is 2, 2. You can check that this satisfies with equality both the constraints x1 plus 2x2 less than 6 and 2x1 plus x2 less than 6. So indeed, it is the intersection of those points. And then the other extreme points are 0, 0, 3, 0, and 0, 3. So indeed, this is an integral polytope. Let's check to see whether it's TDI. And you can guess that the answer is no. The more interesting point, and the reason why the word representation is in the header of the previous slide, is that we can represent this integral polytope in a different way, and so that different representation is TDI. And that is the point, and we just need to be wary of the fact that it relates, that TDI is a property of the representation, not the polytope. Of course, we need to have an integral polytope to start with. Okay, so now let's use the definition. So, for the definition to check, okay, so the question is this, and again, when I say this, I mean this description, not the polytope, right? TDI is a property of A and B, not a property of P. Is this TDI? This is our question. So now let's do what we need to do. We need to look at max of C transpose X. And I'm going to look at a particularly easy C, 1, 1. So max of x1 plus x2 subject to these constraints. So let me write it out. I need to write it out as ax less than b. So A is the matrix 1, 2, 2, 1, minus 1, 0, and 0, minus 1. X less than or equal to B, which is 6, 6, 0, 0. 6, 6, 0, 0. So now it's completely in the form of the definition of TDI, and so I can write its dual. Its dual is minimize 6y1 plus 6y2 plus 0y3 plus 0y4 subject to y1 plus 2y2 minus y3 equals 1. 2y1 plus y2 minus y4 equals 1, and every yi greater than or equal to 0. We can check. Clearly, if I'm maximizing in the 1, 1 direction, then this is the optimal solution where I put that star. So x star is equal to 2, 2 is an optimal solution. But also y star is equal to 1/3, 1/3, 0, 0 is also an optimal solution. And we can also check that it's indeed a corner point, because I have two tight constraints there, and of course these two tight constraints. So I have 4 independent tight constraints. So this non-integral solution is an extreme point. So that means that this is AB is not TDI. Okay, well now let's represent this in a different way. So now let's note that P, which is equal to x1, x2 greater than 0, 2x1 plus x2 less than 6, x1 plus 2x2 is less than 6. I can also just add the constraint x1 plus x2 is less than 4. What is that? I won't make all the tick marks again, but it's basically I'm adding the dashed constraint. This is going through the point. Remember, this is 2, 2. So x1 plus x2 less than or equal to 4 is this constraint. You can call that, it's a redundant constraint. But now let's put this back in and check what the dual is. So let me add that constraint and write down the dual. So in other words, now A is equal to 1, 2, 2, 1, minus 1, 0, 0, minus 1, and 1, 1. And B is equal to 6, 6, 0, 0, 4. So what is the dual that we had? You can compare this to the previous slide. I'm going to have one more variable. I'm going to have 5 variables now. So it's min of 6y1 plus 6y2 plus 0y3 plus 0y4 as before. But now I have plus 4 times y5. And I have similar constraints as before. y1 plus 2y2 minus y3. But now I have my plus y5. Plus y5 because of that one. This has to equal 1. And similarly, I've got 2y1 plus y2 minus y4. Again, my plus y5 is equal to 1. And every yi still has to be non-negative. And, well, now you can check that the constraint, that this has an optimal solution. TDI doesn't require that every solution is optimal. It requires that it has an optimal solution. So and y star is equal to 0, 0, 0, 0, 1 is now an optimal solution. So and indeed this doesn't prove that it's TDI, but it is TDI. It doesn't prove it because I would need to check that this property holds for every integral C. And I just checked it for 1. But at least it takes away the proof that the previous example was not TDI. And now I want to relate this to one other concept that is, again, broader than just optimization, and it has to do with a study of lattices and is more broadly used. And this is this concept of a Hilbert basis. And here's the definition. A Hilbert basis is a set of vectors A1 to AN such that for any vector B that is in the cone of A1 to AN and for which B is integral. So let me just add an aside here so that recall that C is the cone of vectors V1 to VK. This is the set of all vectors x, which equal the sum of lambda I vi, where lambda I are just required to be non-negative real numbers. So this, and if you draw it, you know, the cone of these always contains 0, because lambda I equals 0 is in here, and you can see that basically it allows me to take convex combinations and scaling, so this is why it's called a cone. So recall this definition. So a set is called a Hilbert basis if for any integral vector in the cone, I didn't finish this definition, and B is integral, B is a non-negative integral combination of A1 to AN. And so again, here's an example. C is equal to the cone of the vectors 2, 1 and 1, 2. Essentially what I drew. 2, 1 and 1, 2. Let me draw this a little more carefully. So the vector 2, 1 is here. The vector 1, 2 is here, and therefore C is everything here. And it's saying that if there's that the vectors 2, 1 and 1, 2 form a Hilbert basis if for any integral vector in this cone I can express it as a integral combination of 2, 1 and 1, 2. And you can see that that's not true, because you know the point 1, 1 is, I'm choosing bad colors here. The point 1, 1 is clearly in C, but you can't write it as an integral combination of 2, 1 and 1, 2. However, so this is not a Hilbert basis. But however, C is also equal to the cone of the vectors 2, 1, 1, 2, and 1, 1. And you can see that in this case, I'll take some checking, but you can see that in this case, this is a Hilbert basis. So this is very similar. The reason that this is coming on the same lecture as talking about the fact that TDI is a property of the representation and not the system, and not the actual polytope itself, is the same thing that's exemplified by this by this illustration here. And in fact, this is exactly what we did in the previous slide. We had the lectures, we had the constraints 1, 2 and 2, 1, and we basically added the vector 1, 1. And we obtained a TDI system. So there is lots of literature on Hilbert bases, lots of literature on their exact connection with TDI systems, but I just wanted to draw this. I wanted to draw this connection. We're going to stop here, and in the next lecture, we are going to use TDI to give an important result, which we had mentioned earlier, that arborescences are that the LP relaxation is exact.